managed to lose my compass to this. That's not good. We'll be right back. Okay, well, I guess we can start. Okay, so what am I going to talk about today? So there's a little bit of integrating stuff left, but I thought I'd start on the reaction diffusion equation stuff because next problem set, that's our topic. And so last time I talked about PDEs, like how you discretize them on a grid. And, you know, I was looking around what's a cool setting to explore with partial differential equations. So traditionally, you know, you might do a hydrodynamics thing. So I did write up, you know, Python examples for really very simple, you know, one of the low order integrators, but it wasn't that exciting. You know, you could look at shocks, propagate down a tube or something, but you look at sound waves and see how the boundary conditions were checking, you know, like you could model a trombone, for example, but in 1D. But the reaction diffusion equations are also PDEs, and they're beautiful. They win hands down for cute phenomena. So you know, so that's why we're doing this. It's you know, a simulation of a partial differential equation that gives you some beautiful behavior. So there's so they're nonlinear, and the common ones were first derived from chemical reaction models, and so the chemical reaction and diffusion at the same time. The diffusion thing means that, if you remember the diffusion equation, we talked about last time on purpose. We talked about reaction diffusion equation. This is a partial in one dimension, and there's the diffusion coefficient. So if you if I have something that is equal to this, then the second is negative, so it pushes down. But if it's like this, then it pushes up. So what the diffusion equation does is, so this is a curvature here. You have a curve. So the ascending bumps down, things spread out. So the reaction diffusion equation. So the reaction that gives you spatial, some spatial sensitivity to the spatial. Spatially, you get behavior from the coupling spatial terms in the equations. So theoretically, Turing he wrote this very exciting the source of morphogenesis. So he showed that it was one way patterns. So it was the mechanism for pattern formation in the biological setting. So things like tiger stripes, leopard spots, and the idea is that these reactions would start off in the unstable patterns. And so that launched this whole field of pattern formation research. And there's numerous applications lots of fields, not just So let's so I'm going to talk about Turing, what Turing did actually. What did he actually do? So he looked at things. So you have two concepts. So you have two concepts of things. And they can each have their own diffusion. And they can each have their own diffusion model. So we're going to be using in two dimensions. You could have it diffusion in more than two dimensions. And then there's reaction rates. And then there's reaction rates depend on the concentration. And so there are a bunch of different models. And so there are a bunch of different models for pattern formation. I put one of the cute ones, and I put one of the cute ones. The Bresleder and the gray spot. The Bresleder and the gray spot are pretty rewarding to code up because they give you lovely patterns. So so reactions. So these are chemical reactions. So these are chemical reactions. So this one is the Bresleder model, and there are these coefficients, and this u squared b term is nonlinear. You can kind of see that it's related to chemical reactions because this is a growth term for you. This is a growth term for u, but a removal term for v. So it's like u is grown at the expense of v, and beta grows v. Growth rate. So you can think of v rate for v. So you can think of these as growth and kill parameters. And this term doesn't have any coefficient in front of it, so the whole thing has been normalized in terms of the nonlinear term. So that happens. The Bresleder one. Bresleder. So it's called the Bresleder. The Bresleder. So it's called the Bresleder because it was a bunch of people in Brussels. So yeah, historically. That's why it was. That's why it's got that name. But that's why it's got that. So the main thing I wanted to show you with this. So the main thing I wanted to show you with this is my code that I've given you for the problem set for next week. This is my code that I've given you for the problem set for next week. But so it shouldn't. You get things that look like this. You get things that look like this. So let's run it. Oh yeah, here we go. So So if I stop it. So if I stop I animated it, this sets the initial condition. So I animated and there's a little bit of adjustment for each model. And there's a little bit of adjustment for each model. Nice behavior. So this is just random initial conditions. Nice behavior. So this is just random initial conditions. So this is scale bar up because the animation was hard to get the scale bar to work. So it was hard to get the scale bar as time marches on. So these are different time steps. So these are different time steps. You see some particular wavelength starts to grow in the model. And then it freezes. So after a while, it gets to this point, and then it doesn't change much afterwards. And then it doesn't change much. So some of these models stay unstable. Once they grow, so they're unstable at the beginning. They grow this nice pattern, and this one has stripes. Most
stripes.
And if you adjust the parameters, you can get
different kinds of parameters like
and
spots.
in the brush-later, you can actually get temporal behavior.
In the brush-later, you can actually get temporal behavior, meaning flashing.
Oscillate
like
at you
you
too.
can get it to
It's
oscillate at you too.
Unstable cycles.
It actually goes into unstable cycles as well as making
so those are the kinds of things you get. And
so those are the kinds of things
so one
you
of the
get.
things so I animated this with this you know, this IPython animation package, which isn't really very nice to use, but so you can look at them this way if you want. You can also just print out lots of different images. So here I just print out a bunch of different images. So if you don't want to deal with the animation. Look at images. And so I wrote it in terms of objects, so you can use, you can modify them or use the objects that you want. Then the last thing, so what did I ask you to do? So I asked you to look at the numerical stability. So I'll talk about the scheme. What is the scheme? That's the numerical approximation. And it depends on a time step. If you put the time step too big on the scheme will be unstable. So just adjust the time step until it looks really bad. So that's basically the point of that problem. What about adjusting the horizontal spacing? Whenever you go to a spatial grid, there's a delta x. And I think I set delta x to be 1 in these examples, but you might not want to do that. So ask you
What does
it mean to change delta x?
Explore what
it's equivalent to changing the diffusion coefficients for these examples. So show that. It's not very. And then the gray Scott
much algebra.
And then the greater reaction model for it. And then there are various Laplacian operators. So Laplacian operators go
squared, which is in one dimension is dx squared, but in two is
so you need to figure out how to get that on the grid.
So you need to figure out how to get that on the grid.
I wrote,
and the one that
is the simplest second one. But sometimes people like to use diagonals.
But
so I ask you to modify it to include the diagonals. Yeah.
I ask you to modify it to include diagonals.
If I can what? Oh, okay.
If I can what?
Oh, okay, sure, definitely.
Okay, sure, definitely.
Figure out how to do that.
Let me figure out how to do that.
Mute.
Okay. Better? Okay. Sorry about that. Yes, he says thanks. Hi, Will. Okay, good. Thanks for paying attention. Excellent. Okay, so where was I? All right, so that's the next thing. Then the last thing that I asked you to do is to make a picture that looks kind of like this. So when you look at the model, it has these three parameters, and I wrote them, described them as alpha and beta arbitrarily, gave them labels for feed and kill for the reaction models. And so what I tried to do here is you make a bigger grid, and then you have alpha varying horizontally and beta varying vertically, and there's a little bit of adjustment. How do you get it to look really cool? And this one, I think, this one's the Gray Scott model, and there's some, you have to play around to find, what are nice ranges to give you pretty pictures like this. But it is cool to see the way the patterns change as you vary the parameters in the reaction model. So that's what next week's assignment is about. So now we'll go to here, and we'll pin it. I want to put it on the speaker. So there we go. Not very, oh, you can kind of see that. Okay. So now what I want to do is Turing actually do. So check this out. Eraser. And it works too. Okay. So let's write down one of these models. So I guess I'm going to stick with the Brustleiter model for this example, which looks like this. d del squared u, where the del is ddx squared plus ddy squared. And then we have the reaction terms. And so I guess I can explain what the reaction is. But first, let's write down the Brusseliter model. And then I'll explain how this comes from a bunch of chemical reactions. V, yep, that's right. And dV dt is equal to dV del squared V. So these are the diffusive terms. In the beta minus V. And so this is the Brusseliter model. For reactions that look like this, goes to U. So chemical reactions, so alpha, U, V, and there's one more thing, E, are concentrations of chemicals. And so alpha, you just assume there's a lot of it, so you don't worry about it. Don't worry about it going away. And then there's a reaction that looks like this. So you can see this grows U. Or no, this actually reacts with U to make V, so it's a minus term. It decreases the amount of U that's around. And the amount of V that's grown depends on beta. Doesn't it depend on beta U? Yeah, it does. Depends on beta U. And then we have 2U plus V goes to 3U. And that's supposed to give you this term. And this makes U at the expense of V, so there's a minus sign there. And then there's a removal term for U, which is this 1 here, minus U. So these combined together are supposed to give you the reaction terms. And then if there's spatial degrees of freedom and the chemicals diffuse, that gives you these terms. Okay, so that's where so taking these is supposed to give you that. So, so the first thing we're going to do is look at the steady state model. So this equation, what condition on U and V would give us a constant U and V? So question is, and for the moment we'll ignore the diffusive properties. We'll just say U is constant, is the same value everywhere. And so the question is, what is a steady state solution? So call it U0 and V0. It's a fixed point, so that if I put it in here, I would get du dt is equal to dv dt is equal to 0. So that's going to be the first thing that we want to figure out. I don't really love the way these. You're basically better off just erasing and starting to. Okay, well, I shouldn't erase all that. In any case, what we want is, let's put it back, because we'll be able to answer that question. What is it? It's alpha minus beta plus 1 U, and this is minus U squared V plus U squared. Okay, so if we're looking for a steady state solution, we set this to be 0, we set that to be 0, and we solve for U and V. And so the second equation, so if I can, this means beta minus UV is equal to 0. If I just take away one of those U's, and then I stick
This means I can solve for beta is equal to uv, and so u is equal to beta over v, and I can stick that in there and solve. And what I get is the steady state solution. U zeros and v zero is alpha and beta over alpha. Okay, so that's the steady state solution. So find the steady state solution. And then what we're going to do is now linearize these equations around near the steady state solution. So, so we can think on a plot of u versus v. And I look at a point on u versus v. I can compute du dt and dv dt. And that will give me a direction on this. And if it's a if I'm at the steady state solution, then I won't get any vector. I'll get 0 because the steady state solution by definition satisfies du dt dv dt equals 0. So I can on a plot of u versus v, I can plot vectors and try and understand what the flow looks like. So for any initial u and v, which direction does it go on this plot? And near the fixed point, I can ask things like, is that fixed point stable or unstable? So that's something that we can do. So that's one way of looking at this problem, to try and understand the stability of the system. The other thing we can do is linearize near the fixed point. So we can say, what if the dynamics just barely near this? And we can put in wave-like solutions. So solutions that look like v is equal to v0 plus v1 e to vi kx minus omega t. That's a wave-like solution. Or actually, maybe even better, I should write I kx plus gamma t. That is oscillating in x, and it has some growth rate in t set by gamma. And do the same thing for u. So if there's a, so I can put things like this into this equation. Assume that v1 and u1 are small compared to the steady state solutions, and then look to see what conditions are there on this gamma. So if there are solutions that give me positive gamma, this would grow exponentially. So this is what Turing did, actually. So he linearized the equations, and then he looked for a dispersion relation. So when you come up with an equation that looks like this, or omega k, it's called the dispersion relation. And when you get wave-like solutions, you can look at, does it look like the wave equation, or does it have higher order terms that would give you dispersive behavior? But you can also use dispersion relations to look for when there's exponential growth at certain wavelengths. And so when we looked at that video, you saw, it started off with this random pattern, but a lot of the structure decayed, which is what you'd expect for diffusion only, because diffusion only tends to smooth things out. But then certain wavelengths were unstable, and those were the ones that grew into the patterns that were in the end of the simulation. And so what Turing did is he took models like this, and he showed that there were certain wavelengths that were unstable and tended to grow. And that was then the source of the patterns that he tried, then he argued that this was like a process that happened in a lot of different settings. Okay, so let's do that. So I'll show you how you do this. So so we're going to linearize these equations. So this is something you see a lot in different settings in physics. What do I mean by linearize? So I'm going to try a solution that looks like this. So this is u of x and t. But these
we're going to assume are steady, so they don't depend on time, and we're going to also, so if they don't depend on time, in order for the UDT to be 0, they also don't depend on space. So they're constant everywhere, so this term drops out. So U0 and V0 are independent of time and space. And then we'll put this in, and so this term has a U1U. This is a constant, and this, even though it's got spatial degrees of freedom, this thing, when I take the derivative twice, I'm just going to get a k squared, and then it'll be multiplied by v, so it'll be k squared times u1. It'll have this exponential in it, but this is linearly dependent upon u. Then this is a constant, so if I'm expanding near the steady state solution, all the 0th order terms, meaning, so if I assume this is small, this is a 0th order term, that's a 1st order term. This will be the 0th order term. So this is linear in u. This is not linear in u because it's got 2 u's and a v. So this is like a third order thing. Or it's not third order, but it could go up to third order. Now looking at this equation, 1st order in v, 1st order in v, 1st order in u, and now a nonlinear term. So the only terms that are hard when I stick this in are these nonlinear terms. I have to decide what to do about them. Because all the other terms are going to give me something that depends on v0 and something that depends on v1. So let me show you what to do with the nonlinear terms. And then what will happen is, so we'll put these into this equation, we'll get a bunch of 0th order terms that are the steady state ones, and then we'll get a bunch of 1st order terms, and then we'll ignore all the 2nd and 3rd order terms, things that depend on v1 squared or v1v, u1, or anything that's higher order. Just ignore those. And so we'll only look at the 1st order terms, and that's what's going to give us this dispersion relation, or this, sometimes people call it the characteristic equation. And then we can look at that characteristic equation and decide what parameters, alpha and beta, give us wavelengths that are unstable. So people kind of follow what's going on here. So the technical stuff is not that important. It's the outline. That's important. Okay, so let's do that. So the only hard terms are these these nonlinear terms. So u squared v, I'm going to put in u0 plus u1 squared times v0 plus v1, and there isn't a square. Okay, so that's the full thing. And this has an e to the whatever, that has an e to the whatever, but just ignore that for the moment. I'm just going to write shorthand with this. So this is going to be u squared v0 plus. And then I have, there's a cross term here. So it's 2u0 u1. And I have a v0 term here. And now, so I took the cross term there. And now I'm going to take the 0th order term here and the 1st order term there. So u0, v0. So this is a 1st order term because I have 1 u1 here. And this is a 1st order term because I have 1 v1 there. And now I can write in extra terms, so like u1 squared, but that's now a 2nd order term times v0. So we could do that. We get a u1 squared v0, but this is a 2nd order term, so I don't care about it. And then I can also do u1 squared v, so u1 squared v0, I have u1 squared v1 also, that's a 3rd order term, so I really don't care about it. And so I think that's it, right? So there's like 3 terms here and 2 terms there, I'll get 6. But these are the 1st order terms, right? There aren't any other 1st order terms. Yeah. Yep, it agrees with my notes. Okay, so if I'm doing an expansion here and I want to the 0th order terms will cancel out because we asserted that U0 and V0 are the steady state solutions. And we should be left with first order terms only. So let's do that. Yeah. So I can write out the whole thing. So this procedure where you take a partial differential equation and you linearize it, you'll see this in other settings. Has anybody seen this type of calculation before? Okay, so like the Rayleigh-Taylor instability, the Kevin-Helmholtz instability, there's like numerous instabilities that people do this way. The streaming instability. I mean, in fact, there's a book by Chandrasekhar.
It's just a technique for analyzing like nonlinear differential equations, yeah.
Well,
or like ugly.
So it could have been linear, and I could have still gotten a dispersion relation. It's just it's a PDE that's got partials of various sorts in it. And you either get a wave equation or you get an instability. But the technique where you just linearize, meaning you have some steady state solution plus a perturbative solution, and you ask when does that perturbation grow, or if you're looking at wave equation, how does that wave propagate? So those two calculations are actually the same, but they're both for looking at perturbations around a steady state. So you see this technique in numerous settings, and so oddly, I don't know if you're browsing in the library. I was browsing in the library once, and I came across this book by Chandrasekhar. It's like 200 and something pages. All it was this type of calculation over and over and over again in different settings. So he looked at magnetic instabilities. Most of it was fluids, but it was all the instabilities he could think of. He put in one book. These are basically the same calculation over and over again. So if you haven't seen it, if this is the first time you've seen this type of calculation, you'll see it. Anytime people talk about instabilities, where there's a growth of the perturbation, they often are referring to this type of calculation. Okay, so let's take the Breslater model, and I'm going to write out both the first zeroth and the second order terms. So 0. So du dt I'm going to write with a comma, just in shorthand. So that's the 0th order and the first order term, plus du u, so this 0, comma x plus u 0, comma y plus u1, comma x plus u1, comma y. That's the diffusive term. And so the u0 is the steady state solution, so it doesn't have any time dependence, doesn't have any spatial dependence. So we're only going to be left with those. Plus alpha minus beta plus 1. And now we've got u0 plus u1. And then I've got u0 squared v 0. That's the 0th order term. Plus u0 squared v1. That's the first order, one of the first order terms. And then I have 2 u0 v0 u1. That's the second first order term.
What is your justification for getting rid of the first two u dxx and is that u naught?
Yeah, this is u naught.
Why are you getting rid of those two?
Okay, so u0 is the steady state solution. So it solved the equation with du dt equals 0. And for that to happen, so we solved it assuming that it was constant everywhere. And so that meant that we assumed that it had no spatial variation.
So we assume that like our perturbation for u1 is small enough where everything else cancels.
So we assume that u equals u0 plus u1. So and u0 is the steady state solution that has no spatial variation. It's constant everywhere. Okay? Yeah? Okay. So that's why these terms went away, and this term goes away because we assumed that U0 is a steady state solution. Also V0, right? You need both together. And right, okay, so there's an equivalent equation that looks just the same for V. But let's look and see what we've got left. We've got, we have these spatial terms with U1. We have a time-dependent term with U1. Then we have constant in U0. So these are the 0th order terms here. But we know these have to go away because they're the 0th, they're the steady state solution. So I can get rid of these. Okay. So what's left? So what's left is only first order terms. And what's left is this. U1 comma t is equal to du U1 xx plus U1 yy. And minus beta plus 1, U1 plus U0 squared V1 plus 2 U0 V0 U1. So that's what's left. And we'll get another equation that looks similar by doing exactly the same thing for V. And what's in it is equal to plus beta U1. And I think we just have these terms. U0 squared V1 minus 2 U0 V0 V U1. Okay. So far, so good. Okay, so now we put in our wave-like equations. We put in U1 is equal to some, I guess I call it U1 hat to differentiate it from U1, e to the gamma t plus I kxx plus I ky y. And if this bugs you, you can just replace this mentally with e to the gamma t cosine kxx plus kyy. So just think of that as the same thing. Doesn't really matter. Right, so I substitute this in, and this term will give me gamma times U1 hat times this exponential thingy. This thing will give me a minus k squared, kx squared. Take the derivative of this twice. I get ikx. So I take, and so I get a minus so my ik squared is minus kx squared. So this is going to give me a minus kx squared, and that's going to give me a minus ky squared. And the rest of them are all first order in either U1 hat or V1 hat with this exponential, which, so every term in here is going to have the same exponential. So this was for U, but I need to also have the same thing for V. V hat gamma t plus I k x x plus I k y y. There we go. So all of these terms will have the same exponential term, so the exponential will drop. I can just delete it. It will drop out. So if I do that, I can get gamma times U1 hat is equal to du minus kx squared plus ky squared. Let's move this minus on here. Times U1 hat minus beta plus 1 U1 hat plus U0 squared V1 hat plus 2 U0 V0 V1 hat. And I'll get a similar equation for the second one, for V. which looks like this. Gamma v1 hat minus dv minus kx squared plus ky squared v1 hat plus beta v1 hat minus these things. v1 hat plus the minus sign here. v0, v0, v1 hat. There. Okay, good. So now this is just a matter of grouping. So you can solve for v and then with one of them and then stick it into the other equation, and then you get a single equation for u. And that once you do that, you'll find out that all the u hats, u1 hats drop out. And what you're left with is an equation for gamma as a function of k. So yeah. And so what's it going to look like? And we can redo this. I'll redo this calculation again in a different way. So I'm doing this calculation linearizing by hand and just solving, but you can also write it in matrix form, and then you can write it in terms of the Jacobian of the reaction equation. Yeah.
So the linear terms are the ones that cancel out, but you have to keep the nonlinear terms that still depend on u naught, correct?
So the nonlinear terms, if you have a u squared v term, I expand it out, and then I just take the first order thing.
Okay.
So the terms that were left were u0 squared v1 and 2u0 v0 u1. Those were the two terms left. So so I just assume u is the steady state plus something small, and v is the steady state v plus something small. But I already know what the u1 and u0 and v0, I have numbers for those. Like u0 was beta or something, and what were the steady state solutions?
But my question was more like, you can't just get rid of those ones because they have u naught, v naught, because they also depend on u1 and v1.
Yeah,
correct?
So the two equations depend upon each other. Yeah, and the nonlinear term gives you.
I just wanted to make sure that I was understanding it correctly.
Yeah. So so this is why, the fact that I could have written the whole equation down in matrix form and then used the derivative of the whole thing and written it out as a Jacobian matrix. And then you take the determinant of it, and that gives you the characteristic equation. So it's like, it doesn't actually save you any algebra at all. It's the same amount of calculation. But sometimes when you do this expansion of the nonlinear terms, it's equivalent to taking the derivative on the fixed point. So that's why you can think about it as a Jacobian. It's just that it's a derivative with respect to two things, because you've got a u and a v. Okay, so what you get after a lot of work, well, it's not a lot of work, you get something that looks like this. Times gamma plus c of k equals k. And this is the characteristic equation.
Is kx plus ky?
Yeah, so k squared is kx squared plus ky squared. And so these are functions of k, and v of k, I can write them down. Du plus dv of k squared plus alpha squared minus beta plus 1. And c of k is equal to du dv times k to the fourth plus du k squared alpha squared plus dv k squared times 1 minus beta plus alpha squared. But the reason I wrote it like this is so you can see that it's a quadratic equation in gamma. And so now you can say classify the roots. So you can take the quadratic equation and you can say, when does gamma have positive real components? So if it has a positive real component for a particular value of k, that means it will grow from a perturbation. So I can write gamma of k, let's use the quadratic equation. Yeah. That looks right. So we can solve. So we get two roots. So if the plus root has a real part greater than 0, so let's take the biggest root, real of gamma plus is greater than 0. So remember, our solution looked like e to the gamma t plus ikx plus iky. Oh, let's make this so you can read it. Just like that. So if there's a real root, then we have exponentially growing in time solutions. So that's it. You choose alpha. So the problem with the Bruselator is like lots of parameters. There's du, dv, alpha and beta, and k. And so you've got 5 parameters, and you have to then, so you can plot things as a function of k, for example. So if you pick 4 of them, so you pick alpha, beta, and du, dv. And then you can plot the roots as a function of k, and you can look and see, are there k values that have positive real parts to the characteristic equation? So essentially, this is what Turing did. He showed that there were systems that had these positive roots, and that means positive real parts to the roots, and that meant that when you started off with some random perturbations, some of them would grow, and the wavelengths that would grow would be predicted by this characteristic equation. So essentially, we're following what Turing did when he talked about his models. Yeah, question? Yeah.
So even if the root is imaginary, if it has positive real part, it will increase exponentially.
Yeah. So if it has a negative real component, it just decays to 0. So it would be it would decay down. So the amplitude would decay. If it has a complex thing, it would oscillate. And so it'd be like wave-like. But that doesn't grow, right? So it's stable. Or it's stable. Maybe it's stable is not the right word. So it's essentially the ones with the positive real parts that are the thing. So for the Bruselator model, I didn't find it any easy way to say, well, this region of parameter space and that region of parameter space. And so instead, what I did is I looked for nice parameters that gave you cute patterns. Yeah.
How accurate or how well does the perturbation describe I know there's no general solution, or probably not an analytical one.
No, but so this is a general question for instability models: is you can solve them when the perturbations are small. But does it tell you what's actually going to happen when they're not small? And the answer is no. So then there's like a whole lot, people still calculate in this setting where they try and find out what's the saturation. So you can have an instability, and then the question is what's going to dominate when things stop growing. They may not grow forever. So things like turbulence or turbulence, you can think of it that way. It's like it starts off with instabilities that might cause turbulence, but then once it's fully developed, what sets the spectrum? Or its spectrum would be the amplitude is a function of k, for example. So that would be a turbulent spectrum. As people do things like they try and calculate turbulent cascades, and those models are like maybe good in the linear limits, and then they're not so good when things get big. So we did a first order expansion, which isn't valid if the perturbations get big. So that doesn't mean there's no techniques for trying to solve them, but yeah. So what kind of techniques do people use? So some nonlinear models turn out to be actually analytically solvable, so those get called integrable, and then there are techniques. So things that display solitons sometimes are exactly solvable. Doing higher order things, if they're, sometimes you can do these coupling where you try and balance a set of equations where you have average behavior and something on top of it. So I've seen Eric Blackman do these coupled models for his turbulence models. So maybe that's one way to do it. What else have I seen? I don't know. What do people do when they're trying to find out how stability is saturated?
I just remember hearing that nonlinear PDEs are hard to solve and kind of a pain.
Well, yeah, except for this class of ones that are exactly solvable, and there's like a lot of work on those. Those are not easy to work with, but interesting for their own sake. Yeah. And people argue that they're so the class of ones that are that show solitons and are solvable, exactly solvable, which means you can predict their solutions analytically in some sense with some kind of scattering theory. People argue that they represent behavior of a large class of models, even if they're not exactly exactly correct. So things like solitons you see in real hydrodynamic settings. So you go to the beach and you see these little waves traveling on. I don't know if you're on the beach and you see these shallow waves coming where they have these step functions and then they overlap. Those are described by solitons. And solitons in channel flow, sometimes you'll see those if you are near a storm drain, for example. You'll see a little bump come by and it will just stay coherently. It won't spread up. I have actually seen for real those solutions. And the beach was shallow. The beach where you have a shallow beach with little waves or steps, like little steps come. Sometimes you see them hit each other, and then you'll see behavior where they get stuck, and then the next wave will go. The two-dimensional behavior is pretty amazing. I don't know. This is what happens if you're sufficiently nerdy and on the beach. Everybody else is like, let's go play in the sand. And you're going, wow, look at all those solitons. Like that.
You did a Caltech, just a decent look at waves.
Well, yeah. If you're sufficiently distracted by something that nobody else necessarily can appreciate. It's okay. Beach waves. And channel flows. Traffic flow is another one. Yeah, traffic flow. That one's another one that can distract you with nonlinear equations. Okay, so where was I going with this? Yeah, okay, so that kind of sketches out the setting. So is it easy? I tried to come up with, for the Brustlater model and the Gray-Scott model, how easy is it to classify? So you've got these four unknowns. So you've got du, dv, alpha, and beta, and then k. So if I pick three of them, and then I can make a picture of the fourth one versus k, then you make a plot. You can make a plot and plot the real of gamma plus. So I did that in here with a few examples to see. And so for the nice patterns, which are the ones that I suggested you start off for the problem set, they happen to be in these locations where you get growth, fairly quick growth of patterns that fit on the grid. So the other thing is you're kind of adjusting du and dv to give you patterns that fit on your space. And since I set delta x to be 1, the length of the grid is n times 1, actually, in x values. So rather than picking the length of the grid to be 1 and then setting the diffusion coefficients to be much smaller, and then delta x would be 1 over n. So I did it that way, but you know. So, and yeah, so the answer is yeah. So if you want nice pictures, you adjust the parameters to get you in a region. But it's not all that easy to classify it, meaning these polynomials are kind of yucky enough that, and the space is big enough that it's not like a simple one-line thing to say you need this regime. So maybe if you thought about it, and I'm not sure. So one thing I didn't go look up is which reaction diffusion equation model did Turing actually use? So he wasn't using the Brustlater. he did something else. Brustleter's later. So so I think he was working with a different model. I'm not sure which model. But go look up which model did Turing actually do this calculation. So the Gray-Scott kind of different set of reaction equations, similar type of behavior. So yeah, so one more thing I wanted to talk about is the temporal behavior. So, and this is cool for other reasons. So with a temporal behavior, so we can have an instability in space, which is what we just talked about now. But we could ignore the spatial diffusion part and then look at the nonlinear equation and look at, is there instability in time? And I noticed that it was there just when I was like doing these parameter sweeps, and in some places you'd see it start to flash, and it would just stay flashing. So yeah, so some nonlinear PDEs. So this is in this general class of things that people call pattern information models. Some of them will always decay, so they're generated from they're called potential models, and you can show that the du dt will always decrease, and so that means there's no possibility of it making an endless oscillation because kinetic energy always dies down. But other types of pattern formation models aren't potential models, and so that means they don't have this kind of conserved energy or this decreasing. It's a decreasing kinetic energy. So that means they can start flashing. And so then the question is, well, how do you determine when? Is there any way of determining when something will start flashing? And there is. So that's kind of cool. So I'll show you how to do that. Okay, so let's see. Do I want to start and redo the linear analysis? Yeah, I probably want to redo the linear analysis. Okay, so yeah, so let's look. I guess I don't really need to redo the linear analysis, but what I need to do is write it in a different way. So, so one way we could write the Brustleter out, we could write it like this. So this is the reaction equation, and likewise dV FV. And so in matrix form, so let's write this in vector form. So let's make a vector that looks like UV, and then we could have du dV L squared of this thing. So I guess maybe I'll write it just like this, V. And now I've got this FU and F. So actually, probably what we could write this as a matrix where it's d dx squared. This is a del, right? So we could write this out as a matrix. But the thing that I want to do now is let's look at expand this and this near the steady state solution. So I can write f of u comma v is equal to f u of u0 plus comma v0 plus df du. And now I have a delta u, so this is u minus u0. So this is just a Taylor expansion. xv u0 v0 v minus v0, right? Yes. So so if I had u is equal to u0 plus u1, then let's take this and make it u1, and this is now v1, like that. And likewise, we can do the same thing for fv. fv of u0, v0, these are v's. Okay, so if we think of u1, v1, this we can multiply by a matrix that looks like this. And this matrix is evaluated at u0, v0. So I can write that f, so this f vector, fu, fv, at u0, uv is equal to fu, fv at u0, v0 plus this thing. So this is this vector of the reaction rates at u and v. This is the reaction rates at the fixed point, plus this thing is the Jacobian matrix. And it's evaluated at the fixed point, and then this is how the distance from the fixed point. So you can do, so we could have redone our analysis we did previously by just taking the first derivative term. It's like the first term in the Taylor expansion, but with the multivariable v, so we use the Jacobian. So for the Brusselator model, what's the Jacobian? It only depends on the reaction rates. So these functions fu and fe. So the Jacobian evaluated at the fixed point, and I need to evaluate it at u0, u and v0. Looks like this. Minus up. Doesn't depend on u or anything because I evaluated things at the fixed point, so it only depends on the coefficients of the model. So yeah, so let's ignore the spatial stuff and look at the differential equation near the fixed point. So we have this ut. So if I remember, if I write u is equal to u0 plus u1 and v is equal to v0 plus v1, then I can write du dt, the fixed point solutions. If I expand this out, I get du0 dt plus du1 dt is equal to, now I need to expand this out, and I get f of u of u0 v0 plus j dotted. So it's actually this term plus that term, this term times this plus that term times that. This term goes away, and this term goes away because that's the fixed point solution. So what I'm left is this. Like that. So it's not just j, it's the terms. Let's write it out. d fu du times u1 plus df u dv times v1. But I can rewrite the whole thing, something derivative respect to time is a matrix times the same derivative, or the same vector. So why am I doing this? So the question is, what's the behavior look like next to the fixed point? And so in order to figure out the behavior next to the fixed point, it really comes down to figuring out what's going on with this Jacobian matrix. Because the dynamics next to the fixed point only depends on the Jacobian matrix. So what do you do to classify the behavior? With so this is a vector is equal, time derivative of vector is equal to something times a matrix times a vector. Does anybody want to suggest what we're going to do to classify the behavior? Yeah?
Determinant.
Yeah, so you want the eigenvalues of this matrix. So the eigenvalues will tell you which directions you get, things just move constant, and it will tell you whether you get oscillating solutions or whether you get exponentially growing solutions or you get contracting solutions. And so it comes down to if you have real eigenvalues, if I have a +1, then things will exponentially grow. If I have a -1, things will contract down. You can have a plus and a -1, and then it's like you to get one direction, it would shrink down, in the other direction, it would grow. That's like a hyperbolic fixed point. Yeah?
That's supposed to be a V1
This is
on the left-hand side.
Yeah, it is.
Okay.
It's not a U2, it's a V1. Yes, you got it. So this is the same vector here. Yeah, so the dynamics of that fixed. So this is this general question of any dynamical system in 2D. You look at a fixed point, you go find a fixed point, and then you say, what's the dynamics near the fixed point? It comes down to figuring out what these eigenvalues of this matrix are. So so there's a bunch of possibilities. So I can draw it without actually showing you what they turn out to be, but what are the possibilities? So we're just looking at the reaction diffusion equation now without the diffusion parts. We're just looking at what's the behavior near the steady state solution. So here's a fixed point. So one possibility is you get things that look like that. Things spiral out. So this has a fancy name. It's called an unstable spiral. And the Russellator model has, for certain values of alpha and beta, you get unstable spirals. So if you start off the dynamics very slightly distant from the steady state, it'll go away from it. It'll circulate and go away from it. You also have steady attracting spirals. So these are stable spirals. So the circulation you get when you have complex components to the eigenvalues. And you can also have like a harmonic oscillator where you have a fixed point, it just oscillates around it. So this one is called a center for some reason. Then you've got nodes where everything attracts. So those are called stable nodes. And then you have unstable nodes where everything leaves. And then there's the hyperbolic ones where things come in and they leave in a different direction. So those are the hyperbolic ones. They get called saddle nodes. So if you choose alpha and beta correctly for the Russellator model, you get this. And I gave you the condition for that to happen. Based on the eigenvalues. So let's figure out what it was.
So the eigenvalues tell you what behavior you can expect?
Yes. So this is, you have to classify the behavior of the fixed point. And so these are all, like this one you have, the real part is positive and they're two complex parts. This one, the real part is negative, so it's a tractor, things shrink. These, they're both complex, but positive and negative complex. This one you have one real and one real positive and one real negative. And these are all the non-degenerate ones, because there's degenerate ones too. And it's like you can go further on the classification. Then this is the stable nodes are all real but all negative, and then the unstable nodes are all real and positive. They're both real and positive. So what's the condition? So let me go find the condition because I actually worked it out. The condition is 1 plus alpha squared is greater than beta is greater than 1 plus alpha squared. So it's kind of tight, actually. You have to kind of adjust things quite right. So now let's go back to the UV plane. Here's our stable fixed point. We know things are doing this in the center if we adjust the parameters just right. Then what happens at large radii? Well, at large radii, things tend to attract. So you've got things attracting, and you've got things pushing out. And so that means somewhere in the middle, there is a happy orbit. And that orbit, so what happens is if you start off somewhere, things will spiral out and they'll get onto this orbit and then they'll stay there. They'll just keep going around. So it's not a fixed point, so it has to move. It just keep oscillating. And if you start it out here, it'll spiral in until it gets on this loop. So this loop has a nice name. It's called the limit cycle. And so if you pick the Brustolator model with this range of parameters, there is a limit cycle, and you'll see U and V go around this loop forever, independent of where you start. You know, you either spiral in, or it'll spiral out and reach it. And that's what you see when you see it start to flash. Locally, that's what it's doing. It's going on one of these limit cycles where U is going back and forth forever. So that when you tune, say you fix alpha and you tune beta, you'll go through this region. So if you adjust your alpha and beta parameters right, you'll see certain regions start to flash. But this idea of you have a parameter and you vary it and you see this change in behavior, it's like a bifurcation. It is a bifurcation. So this particular type of bifurcation is called a Hopf bifurcation. And it gives you the birth of a limit cycle, which is this periodic behavior that's from the nonlinearity of the dynamical system. Okay, so right. Okay, so that's like a lot of details. Does anybody have any questions? So this is like the theory, all the theory I can think of on the reaction diffusion equations. Does anybody have any questions on that? Because the next step is to come up with a scheme to simulate it, to explain the scheme.
You gonna have time for that?
No, probably not. So maybe we should end. Yeah, okay, we'll end. The scheme is going to look exactly like what we did last time, where we discretized both in time and space. So it's the PDE is going to have this DDT thing, and we'll discretize it to first order using Eulerian. And then the del squared will use the simplest possible, spatial approximation for that. And then what other details you need to know? Oh, just that because it's a diffusion equation, it's going to have the CFL-like stability condition that we talked about last lecture. Although I'm not going to derive that with the stability in a von Neumann analysis, but that's what will happen. Okay, so does anybody have any more questions? Since we really are, yeah, probably now is a good time to end. Next time we'll do that, and then we'll move on. So next week is the reaction diffusion equations. Then the week after, we're going to look at probability. So we're going to start generating random numbers. So we've got the topics coming up are, using the random number generator to give you distributions. So we'll look at random walks because random walks are fun. And then we'll look at the Metropolis algorithm for simulating a phase transition. And then we're on to quantum computing. And then actually the term, so that will take us up to problem set 8. So we're getting right about halfway for the class. So now is the time to start thinking about your projects. So at the end of the term,
you get to pick what you guys want to work on.
How long are you planning to give us for the project?
Yeah, so looking at the schedule, I have to hold my